So we're starting with section 14-4, dealing with potential energy and kinetic energy. So basically, we know that, first of all, let's define potential energy, PE. Potential energy is the energy possessed by a body by virtue of its position or by virtue of its condition, you can say. For example, a rock that's perched up on a mountain or a hill, it has potential energy. Or if you're holding a ball at the top of the building, if you're standing at the top of the building, you're holding a ball, that ball has a potential energy. Of course, you also have potential energy. A spring that has been compressed, right? So that's the spring, it has been compressed, it has a potential energy. Or a spring that has extended has a potential energy. A plastic or any elastic, say a little strip that you bend, right, now has at this location, it has a potential energy. Okay. These are the more typical cases we'll be dealing with in this section. Similarly, kinetic energy is the energy possessed by a body by virtue of its motion. So if a body is going at a certain velocity, it has kinetic energy. So let's look at the formulas. So for potential energy is mgh, or weight times height. And now if you draw an analogy between this and work, right? I'm trying to show that work and potential energy, they're similar to each other. Weight, mg, you can think of ma, that is the same as force, right, times height, you can think of distance as, right? So that's work we have defined this way. Kinetic energy, on the other hand, the formula looks like this: half mv square. So half times the mass times velocity square. So just to think about it in this sense, if you have an object and you want to give it some kinetic energy, then you're better off increasing the velocity than increasing the mass, right? Because when you increase the velocity, say you double the velocity, you increase its kinetic energy by 4 times, right? Because everything is squared. If you increase the velocity by 3 times, now you have 9 times more kinetic energy. Whereas if you were to increase the mass, double the mass, you only get double the kinetic energy. So something to think about. Okay, what about the units? Because these are all dimensionally the same, if you go back to dimensional analysis, these are all dimensionally the same. They all have same units, right? Newton meter, or foot pound, or pound foot. Okay. Alright, so with this, let's do the first problem in this section. The problem is 1431 in your book. I will read out the problem. Determine the kinetic energy of a truck weighing 40 kilonewton. Right? So weight is 40 kilonewton. So that's equal to 40,000 Newton. Traveling at 25 meters per second. How high would the equivalent amount of energy lift the truck? So if you were to convert this kinetic energy, which comes by virtue of its velocity, if you were to convert that energy to somehow lift the truck up, how high would it be lifted up? Okay. Alright, So let's solve this problem. Now we know that the formula for kinetic energy is half mv squared, right? So half m is 40,000 Newton is the weight. You have to divide it by the g value. So here we divide by 9.81. So this part is the mass, okay? And then here we're going to write v squared, so 25 square. So we get a big number when we do this. I'm going to write it out. Joules, okay? All right. Now, the second part of the question is, if you were to use this kinetic energy as a potential energy, how high would the truck be lifted using the same amount of potential energy? Okay. So here it is. GH. Okay. So here we have 1274,218.75 equals to the mass again. Instead of converting mass and then converting it into mass and then multiplying 9.8 again, what I'm going to do is take a shortcut. mg I know is 40,000, right? So I don't have to do 40,000 divided by 9.8 times again 9.8. That's redundant. Times h. Okay, h is the height to which it could be lifted up using the same amount of potential energy. Okay, so when you divide this thing, you get h equals about 31.9 meters.